All right. So we are doing flow rate sensor calibration this week. So it's another lab where you will have a report. Um, I'll try to go through it fairly quickly, not take up a ton of your time. Um, so the general format and everything is going to be exactly the same. So all the same sections we're going to be looking for. Um, Very similar to the writing we expected you to do on the granular flow lab. This one has different things as far as the calculations you'll be asked to do and all that. I'll go through that in a minute. Um, so let's get started here. So this is the flow system we'll be looking at. This PowerPoint is on Canvas, by the way. I published it today, so you should have access to it. So we have a water accumulation tank right here. We have a couple of pumps. We're only using one of them in the lab. So the tank is connected to our pumps, which force water through this loop. So we have a sensor right here. This is a vortex shedding meter. We have a sensor right here. That is a magnetic inductance meter. And then we have this sensor here, which is a rotometer. So we have 3 flow rate sensors. They're all in series. So the water has to flow through one, then through the other, then through the last one. So because water is not compressible, they're all experiencing the same volumetric flow rate. So the same volume of water is flowing through each sensor. So the main purpose of this lab is to, one, look at how some different volumetric flow rate sensors operate and understand the theory behind them. And then we're going to use one of the sensors as a standard and calibrate the other two. So you're going to go through the calculations required. You're going to see how you do a basic, like, direct comparison calibration. And the conclusion or the objective of the lab is to, one, produce these calibration functions for the 2 sensors that are going to be calibrated, and then to determine whether those calibrations fall within the manufacturer specification or not, so whether it's a good calibration. So the first sensor I'm going to talk about is the rotometer. It's this vertical column. So this is a completely analog sensor. So the other 2 sensors require power. They are electronic, which is good in that it makes it easy to collect data from them because you can hook them up to a computer and directly record the output of the sensors. On this, though, because it's purely analog, it means it doesn't require any power for it to run, but it means that you have to physically look at it, and it would be very difficult to input this data automatically, to collect it automatically. So the way the rotometer works is this white thing here is like a bobber, I guess I'll call it. So it is sitting in the flow path. So it's a vertical column. This thing has some weight, and then you'll notice it's also got a spring here that pushes against it. So as water flows through this thing, it's flowing from the bottom to the top. The drag on this element causes it to rise in the column. So it's being pushed up in the column by the drag force and the water flowing over it. So we can then read what flow rate it's measuring based on this black line on the bobber and where it lines up on these graduations. So right now, where this picture is taken, it is right over a graduation line right here, which would be 7 gallons per minute. So this is a picture of the rotometer reading 7 gallons per minute. So yeah, completely analog. You look at it and see what flow it is measuring, and it's this drag force versus its weight and the force from that spring is what's balancing out. So you're balancing drag with weight and that spring force to get a reading. All right, so then there's also a vortex shedding meter. So it is an electronic sensor. I've given you a picture of the sensor showing its model number here if you want to look it up. There's also a picture showing what the actual, it's got an LCD display on it, so it displays gallons per minute directly as a number. It also shows you the temperature of the water. So this requires power. So it's, if I remember right, it runs on, I think, anywhere from like 15 to 30 volts. And I think we ran it at like 20, just for ease of setting up a number. So you're sending positive and ground to it. And then you could also, if you didn't want to just read it, if you wanted to have some sort of data collection, you can output its reading, and it outputs in current. So it's got some current range that it'll output at, and that corresponds to the range of flows that it can measure. And so you could convert that current into the flow rate that it was measuring if you were collecting it in some sort of data acquisition system. So the way a vortex shedding meter works is you have some element in the flow path. I call it a bluff body. So you've got something sticking up in the flow path. So as water flows over that, vortices get created. So it's disturbing the flow. So downstream from that, you get little eddy currents, little like curls, and they're going to alternate sides of that bluff body. So the vortexes get created, and then they get carried downstream by the flow. So the vortexes are moving at the speed that the liquid is flowing at. So downstream from that bluff body, there's a piezoelectric element. So piezoelectrics emit a voltage, or they have an output when you get strain on them. So sometimes you will see like load cells, if you're measuring very small loads, will be made of piezoelectric. So when you press on them, they have an output. So these are set up so they eddy currents, it's a very thin piece. So those vortexes cause it to bend, and it causes it to bend in opposite directions. So the sensor is actually picking up essentially like the frequency that that thing is bending at. So the faster the water's flowing, the faster those vortexes get carried downstream. They're alternating sides, so the faster that piece ticks back and forth. So it converts that electrical signal that's coming from the piezoelectric into gallons per minute, and then for the data we've given you, we've just read it directly off of the LCD display on the sensor. The third sensor is the magnetic inductance meter. So it is also an electronic sensor. It runs on the same supply voltage that the vortex shedding meter does. And it also has an LCD display that shows you what the measured flow is, and it's also set up in gallons per minute. So the magnetic inductance meter works on something called the Lorentz force, is the basic idea of how it works. So it's set up like this. You've got water flowing through the tube. You've got two coils of wire that are used to create a magnetic field between them. So the Lorentz force is minus Q times V, so charge times velocity, crossed with a magnetic field. So your flow has positive and negative ions in it because it's not pure water. If it was pure distilled water, it wouldn't have any ions on it, but it's got ions in it. So that flow has positive and negative charges in it. So they're moving at the velocity that the water is flowing through that pipe. Then you have a magnetic field. So the minus QV cross B gives you a force. That's the Lorentz force. It happens anytime you have a charge moving with some velocity through a magnetic field. So positive charges get a force in one direction, and negative charges get a force in the opposite direction. So they get split to the two sides of our pipe here, and there is a sensor that can pick up and measure what that voltage difference is between the two sides. So the faster the water is flowing, the faster those charges are moving, the stronger that force is on those individual charges. And so you get more separation and you measure a larger difference in voltage across the thing. So that's how it's relating the speed of the water to the output of the sensor. So that voltage difference gets bigger the faster the water's flowing, and then it turns that into the flow rate. So this sensor, the magnetic inductance meter, is going to be the standard. So the standard is what we're using to calibrate the other two sensors. So the rotometer and the vortex shedding meter are going to be calibrated to the magnetic inductance meter. So what that means is we're going to say whatever the readings that came out of this sensor are the actual flow. That's what the flow was. And we're going to try to force the other two sensors, we're going to calibrate them so that they read the same thing that this one did. That's the idea of how you do direct calibration. So we're going to say this thing had the correct measurement, and we're going to try to add a correction to these two sensors to make them read the same as this one. So how do we do that? So here is our basic calibration function. You're going to plot on your vertical axis the output of the magnetic inductance meter, whatever your standard is on the vertical axis. And then you're going to plot all of the uncalibrated data points from whichever sensor you're trying to calibrate on the x-axis. And then if you do a basic linear fit on that, it's going to give you what your calibration equation is, your calibration function. And we call that fcal of x. So you plug in your uncalibrated numbers for x, you get your a and your b from your fit, and if you apply that to every data point, that gives you your calibrated readings for that sensor. So we're also going to have to talk about uncertainty. So uncertainty is not the error. Uncertainty is like your confidence in the measurement. So each of these sensors has a manufacturer claimed uncertainty. So an uncertainty that the manufacturer says that that sensor will have. That's like the maximum amount of uncertainty that is considered acceptable for that particular sensor. Okay, so for the rotometer, it's 5% of the full scale, and the full scale is the maximum flow that it can read. So for the rotometer, the max flow it can measure is 10 gallons per minute. So its uncertainty is 5% of 10 gallons per minute. So 1% of 10 would be 0.1 gallons per minute. So 5% is 0.5. So the uncertainty of the rotometer is 0.5 gallons per minute. So the vortex shedding meter and the magnetic inductance meter have different max flows that they can measure. So pay attention to that. The full scale is not the same for all the sensors. The full scale is the max value, the max flow that that individual sensor can read. So for the vortex shedding meter, it's 2% of 26.4 gallons per minute. And if you look at it, it ends up being just slightly more than that because, again, 1% would be 0.264 gallons per minute, so 2% is twice that, so it'll be just over 0.5. So the magnetic inductance meter is our standard, so that's the uncertainty in the measurements of our standard. And if we look here, that's what this value is going to be. This is del standard. This is the uncertainty of the sensor that we're using to calibrate. So if you want to think about uncertainty here, this is, I'm going to show you the equations to calculate all of this. But what this is saying is, if we do some calibration, you've got to at least have the uncertainty of the sensor you use to calibrate. So your uncertainty can't be less than whatever you used as the standard. So for the magnetic inductance meter, it's 0.8% of the measured flow, so whatever the actual measurement was, plus 0.5% of the full scale. And for that one, it's 13.2 gallons per minute. It's the full scale for the flow meter. So this is a little bit more complicated to calculate. When it comes to calculating this, so this is going to be the uncertainty of the magnetic inductance meter. I want you to use, for your measured flow, I want you to use the highest flow that was measured by the magnetic inductance meter. Whatever its highest flow number was, times 0.8% plus 0.5% of 13.2. That'll give you a number in gallons per minute. That's what your del standard should be. Okay, so then these del A and del B numbers. So these are the equations for them. And if you look in your lab manual, there is an appendix. Appendix A has an example of the sensor calibration. We go through those equations. You'll have a confidence interval you need to use there. And there's a full example going through a calibration, essentially. You plot standard and uncalibrated and calculate those values. So that is in there. That's in Appendix A. If you want to use that, I would suggest you look through that when you're doing it, just to make sure what you're doing makes sense. So we have these two parts of your uncertainty. You have del A, which is the scale uncertainty, and you have del B, which is the offset uncertainty. So they both include this T value. Now there is a table in the lab manual that helps you find what that T value is. So we're going to be assuming a 95% confidence interval. And then you're going to use this new in there, and that'll be n, which is the number of data points, minus 1. And you'll look up that value in the table, and it'll be based on that 95% confidence interval. If you get confused about that, there is, in here it talks about how to find that. So yeah, it's here. Reading the T table, new is n minus 1, confidence interval 95, so it'll be 1 minus 0.95 over 2 will give you this alpha over 2 number. And then you'll use your new, and those 2 points will give you, there'll be a table, and it's not in here, it's in the it's in another appendix. So this alpha over 2 and your new will give you the 2 spots in the table. You'll match them up. It'll give you a number. So that's what this T value is in both of these. So then you'll also see these SYX and SXX. numbers. So these are standard deviations. So your SXX, notice that it's squared here and not in there, but it is squared there. So just pay attention. It's a sum across all your data points. For the SXX, it's your individual data point. So these are all your X's are your uncalibrated data points, plus your average of all those uncalibrated data points for that sensor. And then you're taking that value and squaring it, and you're going through each data point there. So this is essentially how spread out your data is. Did you take a bunch of measurements that were really close together? That's going to give you less uncertainty because you're doing less, like essentially estimating between those data points. The data points are all your measurements were close together. So you want those numbers, you want these numbers to be small to get a good uncertainty. And so this is looking at how spread out your data was. Did you take a bunch of points close together, or did you take a bunch of points that were really spread out? SYX is comparing your standard. So this is all talking about like this plot is like the Y's and the X's. So the Y's are all your standard data points. That's all the output of your standard, the sensor you used as a calibration standard. This is the result of your basic FCal equation. So that's your calibrated numbers for your other sensor. So this is essentially looking at how close did your calibration come to what the standard was. This is essentially, this SYX is looking at how good was your calibration as far as reducing the error, getting you close to the correct data. So you're going to be using these to find del A and del B. And then they are going to go into this part of your overall calibration equation. So for the rotometer, you should have one of these. And for the vortex shedding meter, you will have one of these. So your X's will be different, your A's, your B's will all be different between those, and your calibration numbers will be different. Del standard will be the same because it's just the uncertainty of the standard, the manufacturer claimed uncertainty of the sensor you used as a standard. So the lab report. So the rubric looks very similar. We do have an updated one, but it's almost exactly the same. Again, the format is going to be exactly the same. So stuff like the background. Oh, and this is actually, yeah, this is still the same flow rate. Never mind. I think we have a slightly updated version. I'll double check that. But essentially, nothing really changes in the rubric. So in the background of this one, instead of going over the steps to dimensional analysis, I want you to go through and explain how each of the sensors work. So you want to talk about the experiment apparatus again. Make sure you do that. So talk about the flow loop. There's a pump, there's a tank, there's the 3 sensors in series. Then talk about how each of these sensors that we're using, talk about the theory of operation behind them. How do they work? How does the rotometer work? How does the vortex shedding meter work? How does the magnetic inductance meter work? Then, of course, your procedure again, the steps that were taken to perform the experiment. How far apart were your data points in general? How many data points did you take? So you're going to look when you see the data that we started from a high flow, went to a low flow number, and then back to a high flow number. So make sure you talk about how we did that. And that's going to be important because one of the things we're going to ask you to talk about is whether you saw hysteresis. So hysteresis is direction dependence of the system. So that's why we go both directions in our measurements of the flow, we want to see if there's a difference in how the sensors read when they're reading flows that are decreasing versus when they're reading flows that are increasing. If there is a difference there, then there was hysteresis. And it means the system behaves differently depending on the direction the system is going. So your conclusions are going to be comparison of the uncertainty numbers. So I want you to compare this, your calculated uncertainty, to what the sensor manufacturer said it should be. So each of these will give you a number in gallons per minute. Oh, and this is actually, there's an error here. This is supposed to be an X here. So that's del A times whatever the actual measured flow was. And that is correct in the manual here. So make sure you're looking at that. And all of this stuff is also in, as far as these equations go, are in the manual for the Lab 5 part of it. But these are, this is an extra appendix that we have where we go through the calibration. So I want you to compare this right here to what the manufacturer says the uncertainty should be. So again, this 5% of the full scale is going to be, for the rotometer, is going to be 0.5 gallons per minute. So whatever your del A is for the rotometer, multiply it by the highest measurement you saw from the rotometer, because that's where the largest error is going to be. Add del B and del standard to that. In your conclusions, I want you to compare, this will be a number in gallons per minute then. All of that together. I want you to compare that to this number, to that 0.5 gallons per minute. Is the calibrated uncertainty less than that? So that's what we're looking for as far as conclusions go. I want you to compare the numbers and then tell me if it was within spec. So you'll say the calibrated uncertainty was 0.4 gallons per minute, and the manufacturer says that it should be no more than 0.5, so this was within spec. So compare numbers, tell me if it was in spec. And you'll do that for the rotometer and the vortex shedding meter. Okay, so make sure you give me table with the raw data. Make sure you give me the calibrated data. So make sure you give me the results of this. So I want to see all your calibrated numbers. Make sure you give me your del A's, del B's, all of your SXX and SYX values. So I want to see these numbers for the rotometer and the vortex shedding meter. And then sample calculations for SXX, SYX, del A, del B. Make sure you give me your calibration functions. So I want to see this full calibration function for the rotometer and for the vortex shedding meter. So other than that, that's pretty much what I have for this one. So again, it's going to be another lab report. It is going to be exactly the same as the previous one as far as the overall format for it. So use the same format file. All the same sections are going to be in there. The big changes are now the background is going to have the theory of operation for the sensors instead of the dimensional analysis discussion. Your procedure should go the exact same way. Look at the lab manual and the discussion about what the procedure was. We should have a video posted of us performing the experiment as well, so you can watch that. Sample calculations, tables and figures. One thing I saw quite a few people do, your figure captions need to be descriptive. So for example, a lot of people in the first lab report put figure 1, pi 1 versus pi 2. And it needed to be something like constant orifice diameter data or something, some sort of descriptive thing, or flow rate as a function of packing height, some sort of words about it, not symbols, some sort of descriptive thing of what that plot is showing. Another important thing to note in this lab, so in the last one, our plots were unitless. They will not be unitless here. Make sure you put units on your axes when you're making your plots. The references section, do an actual reference. Don't just put a link to the lab manual. Don't just say the lab manual was used. Do some, I don't really care which style you use. If you want to use the APA, the MLA, use some actual reference style. Reference it as a book or a journal. The only thing you have to reference is the lab manual, although if you use anything extra, make sure you reference it correctly. If you use any outside pictures or anything like that, make sure you reference them, and then like if it's reference number 2, make sure you put a 2 like in brackets or as a superscript or something saying this is the reference where this picture came from. Okay, so that's what I have for right now. Does anyone have any questions? You can let me know in the chat. So this lab will be due a week from today. So again, it will be due on Canvas as a PDF before our next lab. And as of right now, the plan is we will meet in lab to do the digital to analog conversion breadboard lab. So we'll be meeting in person next week at our regular time at 3:30. So your reports are due on Canvas as a PDF before 3:30 next Monday. All right, well, so if there are no questions, I will go ahead and end this meeting for today. Again, I will post this video really quick. I have a video of me going through in more detail the equations and sort of a little bit more detail about what I talked about here. I would suggest you watch that video, if nothing else, than me going through the calibration equations in a little more detail. That is on Canvas. It's already published. There's a link to it. I would watch that. Otherwise, if you have any questions when you're doing this lab, send me an email. I'll be happy to answer them. And I will see you on Monday.